Hello everyone, and welcome to today's presentation. I'm Pubali Das SarkarAsst, and I will be guiding you through our discussion on infix and postfix operations. This is part of our computer science and engineering series. Today, we'll explore how these operations work, their importance, and how they are applied in computing. We'll look at the concepts behind infix and postfix expressions, their advantages, and how to convert between them. I'm excited to share this knowledge with you, so let's get started. Let's talk about infix and postfix notations. In infix notation, which is what we're most used to, operators are placed between operands. For example, in the expression A plus B times C, the plus sign is between A and B, and the multiplication sign is between B and C. This is the typical way we write math expressions. Now, in postfix notation, also called reverse Polish notation, the operands come before their operators. So, using the same example, it would be written as a BC times plus. Notice how the operator appears after its operands. One of the main advantages of postfix notation is that there are no precedence rules to memorize. Since everything is written in a way that clearly indicates the order of operations, parentheses are never needed. This makes postfix expressions easier to evaluate computationally, especially for computers. Understanding these notations is essential because they form the foundation for how expressions are processed in various algorithms and programming languages. Let's walk through the concept of converting infix expressions to postfix notation. On this slide, we see a table that illustrates some common examples. First, in the infix form, operators are written between their operands, like A plus B when we convert to postfix or reverse Polish notation. The operator comes after the operands, so a plus B becomes a B plus. Now, as expressions get more complex, the order of operations is preserved through the placement of operators in postfix notation. For example, a plus B times C turns into a BC times plus, ensuring multiplication happens before addition, just as in the infix version. When we have parentheses, like in a plus B times C, the parentheses indicate that a plus B should be evaluated first. In postfix, this becomes a B plus C times, reflecting that order directly in the notation without needing parentheses. Similarly, for an expression like a plus B times C plus D, the postfix form is a BC times plus D plus. Notice how the operators are arranged to maintain the correct evaluation sequence. Finally, for more complex expressions like a plus B times C plus D, the postfix notation is a B plus C D plus times. This demonstrates how nested parentheses translate into sequential postfix operations, preserving the intended precedence. The key takeaway here is that converting from infix to postfix involves arranging the operators so that the order of operations is clear and unambiguous, which simplifies the process for computing expressions. This conversion is fundamental for implementing efficient expression evaluation algorithms, especially in calculators and compilers. Now, let's talk about the process of converting infix expressions to postfix. The key here is to use a stack to manage the operators, which helps us keep track of precedence and associativity. When processing the expression, we scan from left to right, and at each step, we decide what to do based on whether we encounter an operand or an operator. If it's an operand, we simply output it immediately. If it's an operator, we compare its precedence with the operator on top of the stack. If the current operator has higher precedence, we push it onto the stack. If it has lower or equal precedence, we pop operators from the stack and output them until we find an operator with lower precedence or the stack is empty, and then push the current operator. This process ensures that the postfix expression respects the correct order of operations, making evaluation straightforward later on. Remember, the main goal here is to efficiently manage operator precedence using our stack, which is central to the overall theme of expression conversion. Now let's look at the key steps in the algorithm. First, we print operands as they arrive, so whenever we see a number or variable, we output it immediately. Next, if the stack is empty or if there's a left parenthesis on top, we push the incoming operator onto the stack. This helps us manage precedence and grouping effectively. When an incoming symbol is a left parenthesis, we push it onto the stack to mark the start of a sub-expression. Conversely, if we encounter a right parenthesis, we pop operators from the stack and print them until we see a left parenthesis, which we then discard. This handles grouping properly. Now, if the incoming symbol has higher precedence than what's on top of the stack, we push it onto the stack. This maintains the correct order of operations. When the incoming symbol has equal precedence, we need to consider associativity. If it's left to right, we pop and print the top operator before pushing the new one. If it's right to left, we push the new operator without popping. This distinction is crucial for operators like exponentiation. If the incoming symbol has lower precedence than the top of the stack, we pop and print the top operator and then reevaluate the incoming operator against the new top. This ensures operators are processed in the correct order. Finally, at the end of the expression, we pop and print all remaining operators from the stack. By then, no parentheses should remain, and the postfix expression is complete. These steps form the core of the algorithm and help us convert infix expressions into postfix accurately and efficiently. Now, let's take a closer look at the process of converting an infix expression to postfix. One of the key requirements here is that we need to know the operator precedence. This helps us decide the order in which operators should be placed in the postfix expression. When we encounter operands, which are usually numbers or variables, we simply add them directly to the postfix expression. It's straightforward. Operands go straight in. Next, when we see a close parenthesis, what we do is pop symbols from the stack until we reach an open parenthesis. This ensures that everything inside those parentheses is processed correctly and maintains the proper order. For operators, the rule is to pop all stack symbols until we find an operator of lower precedence. This means that higher precedence operators stay on the stack until they're ready to be placed in the postfix expression. Then, we push the new operator onto the stack. And finally, when we reach the end of the input, we need to pop all remaining symbols from the stack and add them to the postfix expression. This completes the conversion process. These steps are essential for ensuring that the postfix expression accurately reflects the original infix expression, especially when dealing with operator precedence. Let's take a closer look at how the infix expression a times open parenthesis b plus c times d close parenthesis plus e is converted into postfix notation. Starting with our initial symbol, which is a, we push it to the output. When we encounter the multiplication operator, we push it onto the operator stack. The open parenthesis is then pushed onto the stack, signaling the start of a sub-expression. As we process b, we add it directly to our postfix string. When we see the plus operator, we push it onto the stack, but since multiplication has higher precedence, we keep it on top. Next, we process c and d, adding them to the postfix string. When we reach the multiplication operator between c and d, we push it onto the stack. The closing parenthesis indicates that we should pop all operators until we encounter the matching open parenthesis. So, we pop the multiplication operator for c and d, appending it to our postfix string. After that, we add the plus operator outside the parentheses, which is now on top of the stack, to the postfix expression. Finally, we process the e, add it to the output, and then pop the remaining operators from the stack, which results in the complete postfix notation, a b, c, d, e plus. Remember, this postfix notation, also called reverse Polish notation, simplifies expression evaluation by eliminating the need for parentheses and respecting operator precedence. The infix to postfix conversion follows specific rules, like pushing operators based on precedence and popping them when encountering closing parentheses. This process is fundamental because it allows computers to evaluate complex expressions efficiently and accurately.